Okay, so this is a technique video for how you resolve forces. And I know this can be a bit of a confusing topic, but there is a very simple way to do it, which hopefully, once you get the knack of it, won't ever cause any difficulty again. So I've just drawn a diagram to start with, and I've chosen this 5 Newton at 35 degrees above the horizontal. So when we're resolving forces, we want to know how much of the 5 Newton is going horizontally and how much is going vertically. Okay, now the background to the quick method is thinking about a right angle triangle. So to start with, you sort of think, well, do I do a right angle triangle there or there? Well, we've got the 35-degree angle here, so let's put the right angle triangle in down here. And then we can see that if we think about our normal trig SOHCAHTOA, we've got our hypotenuse, we've got our opposite, and we've got our adjacent. So if I call the x and the y the two sides of the right angle triangle, then we can use trig to work out the x and the y. So I can say that y divided by the hypotenuse is sine 35. And I can say that x divided by the hypotenuse is cos 35. Now, we don't know the length of the hypotenuse, but the thing about resolving forces, and it will also work exactly the same if we're resolving velocities or an acceleration. You know, when you do a projectiles question, you've got a velocity going off at an angle. The technique is exactly the same. So you basically pretend your hypotenuse is the length of the vector. Okay, so the force as a length effectively. Okay, so we've got y over 5 is sine 35. X over 5 equals cos 35, which when you multiply up by the 5, you get 5 sine 35 and 5 cos 35. And you can work those out as decimals. Check you're in degrees. 5 sine 35 is 2.87. And if I do 5 cos 35, we get 4.1 roughly. Now that's fine, okay, and we can do trig hopefully, but what you've actually done is you've worked out the x and the y in this diagram, okay, because the y here, this dotted line, is the same as this side if you think of it as a rectangle. So these are the two components of the 5 Newton force. You've got a 4.1 Newton pulling horizontally, and you've got 2.87 newtons pulling vertically. Okay, that is a bit long-winded for my liking, okay, and it's not the most quick process when you're in the middle of a longer question, so we don't really want to have to think through all of that as we do it. Okay, now the quick way to do it is to think about moving the arrow as if it's a hand on a clock that you can reset the time. So you can actually push that arrow so it points horizontally, or you can push that arrow so it points vertically. Okay. If you imagine twisting this arrow so it sits horizontally in the picture, I want you to look at the 35-degree angle. Okay. What you're doing is you're turning through that angle as you move that. You've moved your arrow 35 degrees. Okay. And what you've done is you've always, when you turn through the angle, you're always landing on the adjacent. Okay. Which means that basically for the adjacent, for the x, it will always be using cos. Okay. Because that was the calculation we did, this one for the x, to work out the adj over the hype being the cosine. Okay, so if you are going to take your arrow and twist it through 35 degrees, you're going to land on the adj. which basically means that you can write down x is 5 cos 35 because you've turned through the 35 degrees. Okay. It will be more clear as I show you a few more examples. Okay. With the other one, I want you, rather than to think about this dotted line, is to think about the length of y there instead. Okay. And think, right, okay, if I'm going to turn the other way and move like the hand of the clock, twist it so you're pointing that way, you're turning away from the 35 degrees. Okay. I don't actually need to do 90 minus 35 to work out what that is. Well, I can do, but I don't have to. All I need to do is think, am I turning through the 35 degrees or am I turning away from it? Okay, so this one is when you turn away from the 35 degrees. Or I'm just going to say the angle at this point. When you turn away from the angle, what you're going to do is land on what is effectively the opposite. Okay, so that is always going to be sine. Now, the very quick way to remember this is just to say, if you turn away from the angle, I want you to think about this little bit of the line as being a little bit of an elastic band. Okay, and you're stretching that piece of elastic quite a long way, because I want you to imagine it's stretching all the way up to there. So you're stretching the angle. Okay, and if you imagine that you turn through the 35, I want you to imagine you are crushing the angle. Okay, those are the two words you've got to remember: stretching and crushing, because stretching is sine and crushing is cos. So that's all you actually have to think about. Are you, as you move this arrow, are you crushing or are you stretching? And you will always end up with the correct trig word. Okay, let's have a look at some examples. Paper stuck together. There we are. Okay, so the first one, we've got exactly the same picture, effectively, just a different angle. All right, so horizontally, we are going to want to know how much is pulling in the horizontal direction. I'm not going to worry about the right angle triangle. I'm just going to literally think about, if I twist my arrow, I'm crushing my angle of 70. So it's going to be 5 cos 70. And vertically, if I turn to the vertical, I'm stretching away from the 70. So that's sine. So that's 5 sine 70. I'm not bothering with the calculator. Okay, same picture, but the angle is marked in the upper position here. You don't have to then think, oh, I must work out this one. Obviously you can. But if this is just labelled as theta, you don't really want to be muddling up with 90 minus theta. So you need a way that will cope with the angle in whichever place it's labelled, and this method does. Okay, so again, if I turn to the horizontal, I am stretching away from the 65. So this time the horizontal is my force times sine, because I've stretched that 65. I've stretched away from it like that. And then the vertical, if I move that through the angle, I'm crushing the angle, okay, as I twist to the vertical. So my vertical is 18 cos 65. Okay, it doesn't really matter which quadrant your arrow is pointing in. Okay, this little sneaky trick, really, because that's what it feels like it is, always works. Okay, so coming over onto this picture, if I want to know how much is horizontal here, I just need to think, right, I'm crushing the 25. So it's 12 cos 25. And then as I move the arrow the other way and imagine twisting it round to point to the top, I'm stretching away from the 25. Remember I said visualize that as a little piece of elastic band that you are stretching as it moves to there. So your vertical is going to be 12 sine 25. And here again, with the angle labelled in this position, okay, shouldn't cause us any problems now. Just think, am I stretching or am I crushing? So this one, to go to the horizontal, I'm stretching my 40. So that's sine. So just think S for stretch, S for sine. And then moving around to the top, it's cos, because we're crushing the angle. So that's 20 cos 40. Okay, we'll do one longer example now. So with this example, we've got more forces. We're going to work out the overall horizontal and the overall vertical force. Okay, so let's do horizontal first. So for horizontal, anything pulling to the right to start with, anything pulling in the positive x direction. Now the 45 is, and it doesn't need an angle, so that's 45 on its own. The 20 is also partly pulling to the right. It's pulling down a bit and it's pulling to the right a bit. So it's going to be resolved around and we're going to twist through the angle. We're going to crush it. So it's 20 cos 15. Okay. The 35 doesn't come into the horizontal because it's just pulling vertically. This 60 Newton force is pulling basically to the left, down a bit and to the left a bit. So we need to resolve this one. So as we twist that around, we're stretching away from the 30, and that would then be sine. So it will be 60 sine 30. So we need to minus that because it's pulling in the opposite direction. And we can work that out on the calculator. So 45, add 20 cos 15, minus 60 sine 30. And that gives us a total horizontal of 34.32. So let's do vertical. Okay, so for vertical, you go up first and then minus anything down. Okay, so we've got a 35 up, nothing else up. The 45 doesn't come into the vertical, but we have these two diagonal forces that are pulling downwards. So again, if we stretch around from the 20, that 15 gets stretched down to the bottom, so it's 20 sine 15. And we're also minusing this one. And when we twist that down to the bottom, we're crushing that angle. We're turning through that 30, we're crushing it. So 60 cos 30. Okay, let's see what this works out as. 35 minus 20 sine 15 minus 60 cos 30. So that goes as negative. So overall it's a downwards force. Let's write it as 22.14 downwards. So what we've done is we've worked out that this means that it is sort of the same as a horizontal force of 34.32 and a downwards force of 22.14. Okay, that's basically what those four forces are the same as. Okay, so an exam question will probably ask you to find then the resultant force overall. Okay, so you have to do the horizontal and vertical, and then you then turn this back into one single force by thinking about the diagonal of this rectangle. Okay, starting from the same point, but coming out to where the corner of the diagonal would be. So let's call that R for resultant, and we just do Pythagoras. And I don't really need a minus because even if I put it in, it'll disappear as I square it. Okay, so 34.32 squared, add 22.14 squared, square root that. We've got a resultant force there of about 40.8 newtons. Okay, the other thing you might get asked is the direction at which this resultant force is acting. So what's the direction, you know, if there's an object that has these four forces acting on it, what direction is it going to move in as well? So unless it specifies, you can choose which angle to do. So I'll normally do the angle to the horizontal. And this is then where you think of your right angle triangle, your 22.14 over there as well. And you can do tan is op over edge. And work out the angle as well. Okay, so that would give us 32.8 degrees. If you've drawn it, they can see where it is, but if you want to really specify, I would say it's below the horizontal, or below the positive horizontal if you really want to be careful about how you're phrasing it. But if you've got the diagram, it should be fine anyway. And obviously if you needed that angle, you could either draw your right angle there, or you could just do 90 minus theta to get the other angle. So hope that helps.